Okay, we're continuing on here. Chapter 17, we got into some electrochemistry. And we were talking about sort of just in general, make sure everybody's on the same page, redox reactions. And remember, redox reactions, basically, we have an oxidation that occurs, which for our purposes usually is talking about losing electrons. There's also a reduction that occurs with it. They always sort of occur together, and somebody will gain electrons. Um, Remember, you can look at the oxidation number to indicate whether or not something is being oxidized or reduced. And again, you can use the basics on a number line to figure it out. If somebody is being oxidized, which means it's lost a lot of electrons or has lost some electrons, it should become more positive. So if you see the oxidation state from the reactant side to the product side sort of move in this direction towards the positive side, that means it's going through oxidation. And if it's kind of becoming more negative, which happens when somebody gains electrons, it is going through reduction. We also have the oxidizing agent, and that is a substance that gets reduced. And we have a reducing agent, which is the substance that gets oxidized. And again, they're called those agents because basically that is the effect they're having on the other substance that's present. So the oxidizing agent is causing the oxidation of somebody else. So they can lose electrons, so it can gain electrons and get reduced. Well, the reducing agent is causing the reduction of somebody else, and that is because it is going to lose electrons, which means somebody will gain them and be reduced. We do have half reactions that we sometimes look at, and that's half of the equation of what's sort of going on. So we could have something like this. And if we see an electron on the product side, that usually indicates this is an oxidation half reaction as electrons are being given off, as opposed to if we see electrons on the other side, uh, maybe here we are seeing electrons on that side, and that is a reactant. And that usually indicates that that is the reduction half reaction that is occurring here. And we can add the half reactions back together. Remember that when we do add the half reactions back together, the one main thing that we do want to make sure of is the electrons should completely cancel out, because that's really what's happening in these reactions. However many electrons somebody loses should be the amount of electrons somebody gains. So they should always cancel out. Now, in some cases, you may have different numbers of electrons in each half reaction. So it may require you to multiply one half reaction by a common number, or sometimes even both of the half reactions by common numbers to get them. But that's the one thing that should always completely cancel out. They should always be on opposite sides of the arrow as well in those half reactions. So these guys should completely cancel out. We finished up talking about sort of how to balance redox reactions in acidic are basic conditions, and a reminder that when we do that, we use sort of the water method to balance, where we add water for oxygen to balance the oxygens. And because we are adding water, again, we do need to add two H pluses to the opposite side. We add the water to balance out the hydrogens that we put there. In addition, if you're starting with more hydrogens on one side than the other, you can start by just adding some H pluses to the opposite side to balance it out. Remember that those things do need to be balanced both in like a normal equation, number of elements, same on each side, and also the overall charge as well needs to be the same on both sides. Questions on that there? All right, so why don't we try one of these? We kind of did one together. So why don't you balance up this redox reaction here in basic conditions and see what you come up with, starting with this guy down here. Okay, let's take a look, see how you're doing. So first we're gonna go through and just identify sort of what's going on in terms of oxidation numbers. So that's obviously -1 there for our iodine. Our oxygen here is -2. There's 4 of them, gives you a -8. Does equal -1 when it's all said and done. So that's a +7 there on the Mn. The I2 is in its natural state, so that is 0. The oxygen here is -2. There's 2 of them, gives you -4. That equals 0 since it's neutral, which means we're looking at a +4 in this situation. So if we kind of look at sort of what is happening on each side here, and I don't erase no 4, there go minus. For the iodine is starting at -1, which would be over here, and ending at 0. So the I is definitely being oxidized. That means by default, this guy is going through reduction, and we see that because the Mn is starting at +7, which is over here, and ending at +4, which is moving in the negative direction. So it's being reduced. That means in this case, the I- is our reducing agent. The MnO4 is our oxidizing agent. Questions on that there. All right, so to balance this in basic conditions, first thing we want to do is just kind of split up into our 2 half reactions. Basically just go same elements on each side, opposite sides there. So we got some Mn in this guy here. All right, next thing we're going to do is balance these just like a normal equation. So everything other than oxygen and hydrogen. So we will need 2 over here for the iodine, and that's about it. Now we're going to balance out our oxygens, and again, we will balance out the oxygens by using water. There's no oxygens on the first one, so we don't have to worry about it. We have 4 on the left on the second one and 2 on the right, which means we do need 2 waters there on the right-hand side. Because we put 2 waters, we will need 4 H pluses to balance out the hydrogens. At this point, we're then going to balance out the charge here. And we're going to look at the overall charge on each side. So here that is -2, and that is 0. That means that we do need 2 electrons in the first one, because that will now give me basically -2 and -2. So that is good. Coming down here, that is +4. That is -1. That's a grand total of +3. That is 0. That is 0. So that seems like an overall of 0 on that side. And that means that we would need 3 electrons over here, which would give me -3, and eventually an overall of 0 on each side. Questions on adding the electrons. So remember, it doesn't need to equal 0 on both sides. It just needs to equal the same number on both sides. And the only way to do that is to add electrons. All right, so I'm just going to get rid of some of this extra writing here, just kind of clean it up a little bit here. Get rid of that, some of those extra numbers. By the way, we also can feel perhaps fairly confident in what we just did because, as we discovered earlier, this is our oxidation half reaction, which means my electrons should be on the product side. This is the reduction, which means it should be on the reactant side. So again, at least we added them to the correct side. We're ready to add these together, but once again, we cannot add them together until we have the same number of electrons. So common number there for our electrons is 6. So we do need to multiply the top half reaction by 3, bottom half reaction by 2, so that we do end up with 6 electrons. So if we do that, 6I minus goes to 3I2 plus 6 electrons. Again, just multiplying obviously this across. Same thing here, we're going to multiply the 2 across, and that'll give me 6 electrons plus 8 H pluses plus 2 MnO4 minus goes to 2 MnO2 and 4 waters. At this point, we should be good to go to add these together. Electrons should completely cancel, which looks like they do. That looks like everything that's going to cancel. So remember that we do everybody on the left stays on the left of the arrow and everybody on the right stays on the right. So we'll end up with something like this. 8 H pluses plus 2 MnO4 minuses plus 6 I minuses goes to 3 I2s plus 2 MnO2 plus 4 waters. Now, if I were to balance it in acidic conditions, I would be done. As you can see, we have the H plus here, and we should be balanced again both ways that we talked about. We have 8 hydrogens on each side, 2 Mns on each side, 8 oxygens on each side, and we also have 6 iodines on each side. We have a +8 from that guy, a -2, and a -8. So that is a -8, that was -6. Yeah, I did them too quick. That gives us a grand total of 0 for the charge over there. And obviously everything on the right-hand side is neutral, so it is 0 as well. So we are balanced in acidic conditions. First off, any question up to there? We want to do it in basic conditions. So at this point, we're going to turn this acidic equation into a basic equation. And this is where we add OH minus to both sides, and it's equal to the amount of H plus that we have. So in this case, we have 8 H pluses, so we're going to add 8 OH minuses to both sides. The side where we have OH minus and H plus will come together to make waters. And in this case, we have 8 waters from that. And usually in this case, that means you could do a little water cancellation. So 4 minus 8 leaves me a net of 4 waters on the left, plus 2 MnO4 minus, plus 6 I minus, goes to 3 I2 plus MnO2 and 8 OH minus. This now should be our equation balanced in basic conditions, as we see the OH minus there. We can verify one more time here. We got 8 hydrogens on the left, 8 on the right. We got 4 oxygens on the first guy and 8 more in the second. That's 12. We have feel like I missed a 2 there. Probably should copy it right. That will probably help. There we go. Now we have the right guy. Missed that too. We got the 4 oxygens in the first guy, second guy there, and 8 on the second, which is 12. We got 2 MNs on both sides and 6 iodides. Overall charge happening here, we got a -2 and a -6 is a -8. And over here, it is a -8. So we are balanced in both ways there. As long as you don't lose the coefficient as you recopy it over there. Any questions on that? All right. Let's just try one more to wrap this part of the stuff up. Let's go to this one, actually. Let's do this one. Let's balance this guy in acidic conditions. Okay, let's take a look, see how you're progressing. So we'll start like normal, kind of just figure out who's being oxidized, who's being reduced. So we did this guy, I think, earlier. -2, it's going to go -14 equals -2. There are 2 of the chromiums there, so each one's going to be +6 to get us there. Our oxygen here is going to be -2, and that's -8. This also needs to equal -2. There are 2 of the carbons there as well. So you can do a little math problem if you need, but that looks like a +3, I think will do it. Then on this side, that's obviously +3, and our oxygen here, -2, gives us -4. This equals 0. That means the carbon here is going to go with a +4 in this case. Questions on assigning the oxidation numbers, which definitely is something you need to be able to do for sure. Again, just figuring out oxidation reduction, all those good things. You could use the number line if you prefer. Our chromium on the left there is +6, and on the right there is +3. It is definitely moving in the negative direction, and that means that it is going through reduction. By default, this guy should be going through oxidation, and we can see it with the carbon. Carbon starting at +3 and ending at +4, which is moving in the positive direction, and it's going through oxidation. That would mean that the dichromate here is our oxidizing agent, and our reducing agent there is our oxalate in this case. Questions on any of that stuff there? All right, so we're ready to balance. We're going to split it off. Chromium with chromium, carbon with carbon. Seems like a good move. And we'll go here. Good. All right, so again, the first thing we're going to do is balance everybody other than oxygen and hydrogen. So we will need a 2 there for the chromium, and we will also need a 2 there for the carbon. That gives us those guys. At this point, we're ready to do our oxygens, and we'll add water, and it looks like in this particular case, we will need no waters on this one, as we do have 4. For the top one, we will need 7 waters, and that's going to get us 14 H pluses. So on the bottom one, by putting the coefficient, it actually did balance out the oxygen, so we didn't need to add any. That then means we are ready to do some electrons here. And overall here, we got a plus 14, we got a minus 2. That's a net plus 12. Over here is a plus 6. So I feel like I need 6 electrons there in the top guy. It's going to give me a minus 6 and a plus 12. Going to net me a plus 6 on both sides in this case. Looking at the bottom here, that's a minus 2. That's a 0. So I'll just turn that into a plus. So we will need a couple of electrons on there. And earlier we saw our chromium was our reduction half reaction, which is good because that's the side we added it to. This was our oxidation, which is the side we added the electrons to. So we hopefully correctly added those. Any questions on that there? All right, so let's get rid of some of these extra numbers so not floating around. We're ready to add these together. We need the same number of electrons, so that is going to require us, it looks like, to multiply the second one by 3. And I'll just write it underneath there. 3C2O4 2 minus goes to 6 CO2 and 6 electrons. Just going to kind of put a line through that one there. I'm going to then add. We should get rid of our electrons. And I think in this case, that is all we're going to get rid of. So everybody on the left will stay there. So 14H pluses plus Cr2O72 minus plus 3C2O42 minus goes to the other side, 2Cr3 plus, 7 waters, and 6 CO2. This again should be balanced in acidic conditions, as we see the H plus there, and should be balanced correctly. So we got 14 hydrogens on each side. We got 2 chromiums, 7 oxygens here, and another 12 there. That looks like 19. And on this side, we got 7 oxygens and 12, which is 19. 6 carbons on each side. Overall charge on the left there, we got a plus 14 from that guy, a minus 2, and a minus 6. So that's a lot of math there, but maybe like a plus 6, I think. That is a plus 6. That is a 0. That is a 0. So we are balanced on each side. Any questions on how to balance these equations, identify oxidation reduction, oxidizing agent, reducing agent, and assigning oxidation states? Any questions on any of that? All right, so this hopefully puts everybody on the same page. Again, depending on Chem 50 you took, you might did a lot of this or not very much of this. So hopefully we'll all be on the same page. Now let's get into really what this chapter is mainly about, which is galvanic cells. And let's talk a little bit about galvanic cells. And galvanic cells are really redox reactions that are happening. So there is sort of an oxidation that's occurring and a reduction that's occurring. And this is a typical sort of galvanic cell setup here that you could build in a lab. You got a couple beakers, and within the beaker, we have a solution. And in this particular one, we have zinc ion solution, which is zinc sulfate. We have a solid zinc electrode that's in that solution. On the other beaker, we got copper ions floating around and a solid copper electrode that's in there. They're connected by a wire that goes through a voltage meter. There is also a salt bridge that is here. And a salt bridge is usually filled with some type of electrolyte solution, some type of salt solution, hence the name salt bridge. Also has a couple of plugs there so the liquid doesn't completely fall out one way or the other. So what happens in this case is we have an oxidation that occurs in this galvanic cell, and that occurs at the anode side. So the anode side is where we see oxidation occur. And in this particular case, what happens is our zinc that's solid will lose electrons and then end up as zinc with a +2 charge and go for a swim in the liquid part. It will give up its electrons, which will transfer down the wire to the other side. And it will head from the anode to the other side where we have the cathode. And the cathode is where the reduction part of the reaction takes place. And on the other side, where in this example we got copper solid and some copper ions in the solution, those electrons will come on in and hook up with the copper that's floating around in the solution. It will reduce the copper, and the copper will get out of the pool, basically, and go over there to the solid. So on this side, we have the oxidation where it jumps into the pool, and on this side, it gets out of the swimming pool and becomes solid in this case. And this process continues. Obviously, those electrons that go out through the wire to do this process can be used to do some type of work and provide obviously a voltage. So on our anode side, we have our half reaction, which is our zinc going to our zinc with a +2 and a couple of electrons. And that is our oxidation half reaction. Like I said, on the other side there, we have our reduction occurring as those two electrons come in and reduce down that copper to solid copper on that side. Again, if you add those together, you get the overall reaction, which is what we see here. It is overall zinc going from solid plus our copper 2 going to our zinc with a 2+ charge and our solid copper in this case. This is going from zinc from 0 to +2. It is becoming more oxidized, becoming more positive. Our copper is going from +2 to 0, gaining those electrons, becoming reduced. Electrons are basically transferring over in this particular case. Now, the salt bridge is an essential part. There is a sort of potential difference between the anode and the cathode, where you can kind of think of the cathode side as being more positive. That's going to kind of draw the negatively charged electrons to the other side. The salt bridge plays a really important sort of function in allowing this reaction to continue. If you pulled the salt bridge, and if you look at the salt bridge, what it does is, for example, over here, is going to drop some positive chloride, potassium ions in there, and negative chloride ions are going to drop into this beaker on the left. So if we take a look at this, just that, we have our two beakers, we have our salt bridge there, and it's got, again, we'll use the one that's in that example there, our potassium chloride in it. And on this one, we had our zinc with our zinc 2+ and our copper with our copper 2+ connected, obviously, through a wire. So as this cell runs, the salt bridge plays a really important sort of procedure here. And as we see here, we have our positive ion going that way and our negative ion going that way. So what would happen, for example, is if we pulled the salt bridge, and let this thing run without the salt bridge, what's going to happen is you're going to get your oxidation occurring over here, which means you're going to get a lot of zinc guys dropping into this solution. And that's going to send perhaps a lot of electrons this way and going to drop into here. And that's going to take out a lot of the positive guys in this solution and leave like a spectator ion in the solution as well. So what happens is we pull it. What's going to eventually happen is you're going to build up on this side a very big positive charge because you got all these positive ions dropping in there, along with the original zinc ions that are in there in that solution. And you're going to build up on this side as you remove all those positive coppers. You're going to have the counter ion in there that's like sulfate or whatever it was in this example, and you're going to build up a really big negative charge on that side without the salt bridge being present. That's not good because negative and negative don't like each other, so these negative electrons are not going to have any urge to go to that side because that's quite negative. It's going to be repelled. In fact, they would actually be more attracted just to hang out over here, right? Because now you got a really big positive charge over here this side. And clearly your cell would stop running and functioning at this point because you have really the wrong sort of buildup. That is why when we pop in our salt bridge or have our salt bridge in there and we have our positive, say, potassium ions going down into there, those positive potassium ions are going to balance out that buildup of negative charge, which we don't want on that side. We actually want a more positive charge on that side to draw the electrons there. And the chloride that heads this way with those negative charges is going to drop the big buildup of positive charge that would occur on the left-hand side, which again, we want more negative. So we kind of want a more negative on the left-hand side in the anode compartment to kind of pull those electrons away while we have a more positive sort of side on the other side to kind of bring them to that side. So the salt bridge plays an important function in allowing those electrons to continuously travel from the anode to the cathode. Without it being present, we would get a buildup of the wrong type of charge on each side of those compartments that we don't want. It's going to inhibit the electrons from traveling. Any questions on that there? All right, so as we can see here, the difference between the electrical potential on between the anode and the cathode is called sometimes cell voltage. A volt is 1 joule of work per coulomb of charge transferred. Coulomb, the unit of electrical charge. So 1 volt is equal to 1 joule per coulomb. Sometimes referred to as electromotive force and or cell potential. So sometimes in problems they'll ask you to calculate the cell voltage, they'll ask you to calculate what the EMF of the cell is, or the cell potential. Essentially, they're all sort of doing the same thing. There's our actual sort of in beaker laboratory one. You can kind of see the salt bridge right there. And again, we have our electrons going through from one side to the next, and we get a positive cell voltage, which is usually pretty good. Now, another way that sometimes galvanic cells are sort of represented is through what is known as a cell diagram. And a cell diagram is basically a shorthand for the reaction that's taking place. We have basically our anode side here with one line separating sort of our reactant and product. We then have this, which represents the salt bridge. And then on the other side, we have one line representing, once again, our sort of reactants and products. So how does this work? In most cases, when you look at a cell diagram, usually this is the order. That's a reactant, that's a product, that's a reactant, that's a product. So as you can see, reactant, product, reactant, and product. So that is, again, how it sort of relates to the equation. Some things that you may see in these cell diagrams, as you can see here, this is standard concentration of 1 molar. If it's not 1 molar, they may also put it in the actual concentrations in there. They may also exclude the concentrations. So if they do, you can probably assume that it's 1 molar. Otherwise, they would put it. You will also sometimes see pressures in there as well, like 1 atmosphere. as some electrodes are gases and our compartments are gases. So sometimes you'll see pressures in there as well. So these two are related to each other, and that's usually the deal: reactant product, and then you can kind of build your reaction from it or equation from it if you need it. Now, one of the things we look at when we look at galvanic cells is something known as standard reduction potential. And standard reduction potential is sometimes abbreviated as SRP. And it is a reduction potential, which means it gives you basically the voltage associated with the reduction reaction that's taking place. So if we look at zinc here, in this case, zinc is our anode, and hydrogen is actually our cathode in this case. And we can see here again, if we kind of look at our cell diagram, this is our zinc going from 0 to +2 being oxidized. This is our hydrogen going from +1 to 0, which is being reduced in this case. Because there is no physical version of hydrogen to use as an electrode, a lot of times they will use something else as an electrode, an inert electrode like platinum. Sometimes they may use something like graphite or something like that as the electrode. So as I mentioned before, you will sometimes see like gases and pressures in these cell diagrams, and they'll also put the physical sort of electrode that's being used in this case. For hydrogen. In this case, it's platinum is the physical sort of one. And once again, it goes the same order. If you look at the overall reaction, reactant product, reactant product. So again, reactant product gives us our overall reaction that's taking place. So again, we see our zinc being oxidized, losing electrons to our hydrogen. So overall, what's happening is we're sending electrons from the zinc to the hydrogen in this particular case. Now, what happens and how do we calculate the standard reduction potential? There's a whole table of SRP values that you can look up, and it's the voltage associated with the reduction reaction when everybody's sort of in standard conditions, 1 molar for concentrations and 1 atmosphere for pressures. So usually when we want to have sort of values to use and maybe we're not really sure what we want to do, they sometimes will call something a standard and compare everybody else to it. So for SRPs, they use the hydrogen electrode as the standard, and they sometimes refer to that as the She for the standard hydrogen electrode. And they basically gave it an arbitrary value there of 0 volts. So they sort of assigned it 0 volts as the standard. And basically what they did is just kind of hook everybody else up to it and measured the voltage, and they were able to figure out the standard reduction potential for all the other sort of elements and half reactions that are going on. So the standard that is used here for SRP is that standard hydrogen electrode. And like I said, they basically just hook it up. Like in this example here, if they take that standard hydrogen electrode and they hook it up with zinc, and in this arrangement here, our zinc again is going to be our anode, and our standard hydrogen electrode or hydrogen electrode will be our cathode. And when they hook that up, they get a cell voltage of 0.76 volts. So they could use this equation here to calculate the SRP for our zinc in this particular case. And this is E of the cell, or the cell voltage, is E of the cathode minus E of the anode. Now, there is kind of two versions of this equation that sometimes people will use. They will use this version here, or they may use E of the cell is equal to E of the cathode plus E of the anode. You may be saying, well, that seems kind of weird. It looks like the same equation, but one's plus and one's minus. And there is a reason why one is minus and one is plus. And as we will talk about what the difference is between these two, I would recommend that some point you just choose one and kind of stick with it so you don't mess up signs when you're doing it. But let's first talk about his cell here. Because it is 0.76, the total cell voltage, they can pop into here 0.76 volts is equal to 0, which is our cathode minus E of our anode. And that will then give us that our zinc guy is going to equal minus 0.76 volts, which will give us our reduction potential here for our zinc. Now, they could also hook it up here for our hydrogen and copper. In this case, though, the hydrogen is the anode and the copper is actually the cathode. And if they do, what we see here is in this particular case, our hydrogen is going from H2, which is 0, to +1, so it's being oxidized. And the copper is going from +2 to 0, which is being reduced in this case. So that's what you see here, +2 to 0, and obviously 0 to +1. Again, by hooking it up and doing the calculation using that formula, they will find out that the SRP, their value for copper 2, is 0.34. Here is a table that has all the SRP values in it, and it's usually one that you have to look up. And let's talk a little bit about when you go to this table and some of the things that you would use. So first off, the E that you see for the reaction is for it as it is written. And since this is a standard reduction potential, you will look and see they all are adding electrons on the reactant side, which means all of these reactions that you find in this table and you look up are all written as reduction reactions. Now, that's important because in an oxidation reaction like we have here, our galvanic cell, we have both an oxidation reaction and a reduction reaction. But you will only find reduction reaction values in this table, hence the name again, SRP, reduction potentials. Now, how do you know if you put two things together, whether or not who should be your anode or who should be your cathode? So if you are not given any information about how this reaction is occurring, you're not given an overall reaction or anything like that, you're just simply told, hey, you're going to build a galvanic cell out of these two things. When you look at the two things that you're going to build your galvanic cell out of, the one that has the more positive E value, SRP value, has a greater tendency to be reduced. So what that means is the guy that gets reduced is your cathode. So the more positive SRP value will typically be your cathode. The other one would be your anode. This again is a situation where you are not given the overall reaction or told how it's happening. If you are given the overall reaction or told how the reaction is occurring, you need to actually look at the equation and decide who's being oxidized and who's being reduced. And that will tell you who's your anode and cathode. So if you have the equation, you need to look at it and decide oxidation and reduction, and that will tell you your cathode and anode. If you're not given the reaction, the more positive SRP value should be your cathode. That will usually set you up for a nice positive cell voltage, which is usually what you're looking for. As we'll talk about, positive cell voltage means spontaneous reaction, so that's all good. That's usually what you're shooting for. Half cell reactions are reversible. If you reverse a reaction, you will change the sign of the E value. And the last thing that's sort of important here is if you need to multiply a half reaction by a coefficient, like we did previously, like we need the same number of electrons, it has no effect on the value that you get from the table. So if you need to multiply that half reaction just to write the balanced equation, it will not do anything to the values that you find here. First off, any questions on that? All right, so now let's go back to that equation I mentioned that could be minus or positive. And let's just Let's just grab a couple from here. Actually, we'll just do those two. I think would be good. Let's see on this page. Yeah. So if we grab these two half reactions here, we'll do the zinc here, I think. So we go to an SRP table here and we find our copper, and it would look like this. And it will have an SRP value of 0.34 volts, right? So positive 0.34 volts. And I think it was zinc on this one, right? Yeah. So we'll borrow the zinc here, minus 0.76. Zinc plus 2 electrons has a value, SRP value, minus 0.76 volts. All right, so these are the values and the two equations that you, for example, would take from the SRP value. And let's just say that we're going to build a galvanic cell where we want to kind of set it up correctly here. We want our anode and our cathode. The first thing that we could look at here is the SRP values. And we would see that clearly here, the copper one is more positive than the zinc. And that should tell us that perhaps our copper should be our cathode, while the zinc here should be our anode again. And that's going to probably give us a nice positive cell voltage as we go across here. All right, now we'll throw a salt bridge in there as well. Now let's get to the actual equation. We want to know what is the cell voltage here for this guy. So we have those two equations, which is E of the cell is equal to E of the cathode minus E of the anode. And you can do this equation where you add it as well. The cathode plus E of the anode. So what is the difference between these two? When I look at the SRP table, they are both written as reduction reactions. In reality, though, in my galvanic cell, my anode guy is where oxidation occurs. And really, my zinc reaction is not this reaction that's taking place. It is the opposite reaction, which is the oxidation reaction. So one of the things that just said is if you take one of these half reactions, you can reverse it. And if I reverse that zinc reaction, I will actually have the oxidation reaction occurring, where zinc is going to give away a couple of electrons. And if I do that, this is no longer the reduction reaction. This is the oxidation reaction. Now, when you reverse a reaction that you take from the SRP table, what happens to the SRP value is the sign changes. So for this reaction here, the standard oxidation potential, which is really what it is, would actually be positive 0.76 volts. And that's really what's happening in this reaction. It is really the zinc being oxidized here. The copper one's good to go because it is being reduced. And that is what will give us really our overall reaction. We would have our zinc, not like that. We would have our zinc that is, again, losing those couple of electrons, going through its oxidation reaction. And our copper, which is gaining those electrons, going through our reduction reaction. Want to put an extra T's where they don't go. And if we added these two half reactions together, our electrons would cancel. And that would give us the overall reaction as we saw, I think, on the previous page there. Our zinc plus our copper 2 goes to our zinc 2 plus our copper in this case, right? Now, if we wanted to calculate the cell potential, we could do it with either of these two equations. And we could do it first off with the subtraction. Even though technically speaking, the anode reaction in our example here, the SRP value should be reversed. If you choose to use the one where you subtract the two values, you should not change the sign that you find in the table. So if I was going to do this with the E of the cell is equal to E of the cathode minus E of the anode, I'm going to put in here my cathode, which was my 0.34 volts, minus my minus 0.76 volts. That is what the subtract is here for, because it is the anode one that always gets the sign reversed. So by subtracting, the subtraction will reverse the sign for you without you having to change the sign yourself. So if you don't want to have to fuss with changing signs, you subtract those values just like that, and it will always change the sign of the anode. Now, if you want to write everything sort of correctly and you want to change the sign for your anode part, then you should add those two values. So if you want to change the sign for the anode, you should take the cathode plus the anode, where you have changed the sign that you find in the table. And then you would get obviously really the same thing, 0.34 volts plus a positive 0.76 volts gives us our 1.1 volt. So it's really up to you. I personally a lot of times use the subtractions. I don't have to worry about changing signs. Just go to the table, find the two things. All I have to worry about is identifying the cathode and anode, and then I could just subtract it. It will change the sign for you. If you want to change the sign for the anode, then you need to add. Don't do both. Don't change the sign and then subtract and put it back. Yeah. So that's why I said earlier you can use either one, but I would probably stick with whichever one you want to kind of stick with. If you don't want to, again, worry about changing the signs, then you just grab the values in the table with the signs they have exactly the way they are. That minus from the subtraction will change the sign for the anode for you. If you do want to change the sign, then you definitely can just add them together after you change the sign and you're good to go. But don't do a combination of both because you will get it wrong. Yeah. Any questions on that there? Here. All right, so let's take a look at one here. What is the standard EMF of this cell? Um, that's made from cadmium and cadmium nitrate and chromium nitrate solution. There's some SRP values here. Why don't you also write the balance equation as well? Identify cathode, anode. Okay, let's take a look since we're getting to the end here. First off, we don't have an overall reaction, so we're basically just going to go to the SRP table, find the two things involved. In this case, we can look at the SRP values, and although they're both negative, this one is more positive. So this guy should be our cathode, and by default, this guy here would be our anode in this case. What that means is, technically speaking, this reaction is not written correctly. If we wanted the balanced equation, we would have to reverse it and give us something like this. And since we did reverse that, that technically would now become positive 7.4 volts for our anode. And if we wanted the overall reaction, we could add these together, but we do have different numbers of electrons there. So technically, we would need to multiply the top guy by 3, and we would need to multiply the bottom reaction by 2. So I'm just going to rewrite that underneath. That's going to give me 3Cd2 plus 6 electrons, gives me 3Cd. Remember that when you do that, it has no effect on the SRP value that you find in the table, so it's still going to be minus 0.4 volts. For our bottom one there, we're going to go 2 CRs, no plus, just arrow, 2 CR3 plus 6 electrons. Also not going to have an effect here on the SRP value. Now we could add these together to get our overall reaction. Our electrons should completely cancel, and that gives us 3CD2 plus 2CR solid goes to 3CD plus 2CR3 plus here. So this would be technically our overall sort of reaction in this case. First off, any questions on that? Also should still be balanced, three CDs on both sides, 2 chromiums on each side. Overall charge on this side plus 6, overall charge on this side plus 6. So again, everything is balanced like it should be. Now, if we want E of our cell, we once again could do either way. So again, if you do cathode minus anode, remember, since I'm going to minus, I'm not going to change the value. So if I did it that way, I would take minus 0.4 volts minus a minus 0.74 volts. Again, that's going to change the sign for me, so I don't have any issues. And that's going to give me a 0.34 volts. Or we could just do what we have here, which is I already changed the sign, so I could just take E of the cell is equal to E of the cathode plus E of the anode, where I have already changed this sign, and just add them together at that point, which is essentially what we did above. And that gives us 0.34 volts. So again, you can do it either way. They both should end up with the same answer, as long as you just don't do them both together. Questions on that there? All right, related